In the last few lectures we have been seeing about the design of combination logic using MSI, medium scale integrated circuits. We used examples of multiplexers, decoders, and saw how to map a given specification, given requirement into hardware using these components. We said that in terms of the number of in terms of the count of the number of ICs, these are efficient because of the small number, consequently leading to smaller size and lower cost, higher performance, and lower power dissipation. But then when the circuit, there's a limitation on these ICs in the sense of the number of gates functions, number of gate functions these circuits can give, because we just roughly remember, we defined a medium scale integrated circuit. It's a circuit with about 10 to 100 gate functions. So when the circuit becomes larger than that, the definition is all right. They are called large scale integrated circuits. But leaving the definition apart, the circuit becomes large. It's not easy to map that during the heuristic mapping, intuitive mapping that we have been doing for the multiplexers and decoders, because there is no systematic procedure, conceptual procedure. So we need to have the usage become inefficient somewhat. So more and more hardware, mapping it in a given requirement becomes more and more difficult in a best possible way. That is one thing. Second thing is, when you have a circuit of that type, large scale circuit, large number of gate functions, it will be nice to have several uses for that. I would like to use it for different applications. I may buy it and use it for one application. Later on I may change the application. I may not drastically change the application. I may change some of the specifications of the application. I may change some requirement. Some of the specifications may change. In which case I don't have to redo it. I will go about and get another IC and then do a different design. If I can make some changes in the design and use the same hardware. This concept is called programmability. Programmability is a very important concept in digital design. That is how we get microprocessors and computers. Today we'll say, programmable logic devices is what I'm going to talk about. PLDs. So the programmability means when a given hardware can be used for different applications by changing the design. In computer, you know that the same computer can be used for different applications by changing the program, by reprogramming it, right? You are not familiar with microprocessors, but microprocessors are nothing but computers again. These are also processing units, just as you have computers. In fact, a computer has a microprocessor. Processing unit of a computer is a microprocessor. The term micro came because it's a small circuit, one single chip processing unit. That's why it's called a microprocessor. So the same application, if I have a microprocessor which is an expensive piece of hardware, I like to use it for different applications by reprogramming it, programming for different applications. These are some of the things I would like to have. So same way I want to extend this concept of programmability to even less extensive hardware, not necessarily that of computers and microprocessors. I may have a piece of hardware, I may want to configure it for an application, I may want to change it for different applications, or even in the same application I may want to reconfigure it for different specifications. I should be able to do it. This programmability helps in using the hardware repeatedly, reuse of hardware, saving costs, and designing an efficient architecture, designing an efficient system, because you cannot always get the best possible design in the first iteration. You may have to iterate several times in order before you can perfect a design. So the concept of programmability becomes important, and added to the fact that when a large system is there, like a large scale integral circuit, mapping is not an easy task, it's not a trivial task. So there again the programmability is there, because I may want to map it and then want to change it, different configurations they made. I want to try different possibilities and finally fix the configuration. See, this software is something which all of you are familiar with. That is, you write when you write a program for a computer, you call it software. Actually, the word software is used by so many people in so many different senses, so many different ways. You really don't know what is the definition of software and hardware and all that. So in between there is something called firmware. You heard of the term firmware? The hardware is, take a computer. Computer is a software, hardware. You have an application program is running in it. Your Word, for word processing. Even the operating system, Windows 2000. This is all software. But then I can, some of these changes, subtle changes that I make for specification changes. Some of these things are not changed very frequently. I can change it, I put it there, and then if I have to change it, I may have to redo it. It is not like software which for the same computer, on the same day I can use different software for different times. Even today's computers, I can run several software in parallel, multitasking they call it. Multiple processing of multiple programs. Whereas in a firmware, the configuring the computer for a particular use requires certain programming. The programmability that I was talking about comes under that category. That's why I'm introducing the word firmware, because this is not the program that you are familiar with in a software sense. Programming is not programming in the software sense that we are familiar with. From a day-to-day point of view, when somebody says software, you understand something. You understand a word processor or a database application. I don't mean programmability in that sense here. The programmability required for reconfiguring it. For example, a computer will be reconfigured for certain applications, certain class of applications. This comes with the system program, but I may change it. If I change that firmware, I can change it. Firmware defines the usage, the available resources of the computer on which you write the software to run for different applications. So when I say programmability, I mean programmability in that sense of firmware here. So I may have a piece of hardware in which I can change a part of this, either replace it by another hardware, a hardware which has a program, I throw it out and put another piece of hardware which has another program, or use the same hardware in which I will erase the program and then put another program. This programmability, this level of programmability is the firmware. Okay, this is the point, subtle point. Now, as I said, we already made a case for the reason for programmability, and programmability in a micro sense here, not in an application sense or a macro sense. They were originally devices known as PROMs. There are many devices which are programmable logic devices. First one is a PROM. PROM stands for programmable read-only memory. ROM stands for read-only memory. Programmable read-only memory is a PROM. See, as I said, we are interested in combination logic and sequential logic. That's all in this course. It's a basic digital design course, first level course on digital design. I'm not interested in a computer or microprocessor programming languages and programming skills and all that type of. To that extent, how is this ROM going to be helpful in a programming, in firmware? Now, basically in all these designs, either it's a combinational design or a sequential design where a combination logic is used for steering, We have a truth table which has to be implemented. You call it transition table, you call it state table, whatever table. There is a truth table which has to be implemented. There is an input and an output relationship, and we simplify it using corner maps and then get the minimum possible hardware. Instead, I want to implement the truth table directly in hardware. That is a read-only memory. A read-only memory is nothing but a hardware truth table. If I can etch the truth table in hardware, in silicon, then it becomes a ROM, because each of the possible inputs, each of the possible combinations of inputs should produce the corresponding output. That is the truth table. So the ROM will have inputs, the three inputs, let us say A, B, C, and each of these inputs, they may have certain value stored in it for that particular combination of inputs. Outputs, these are the outputs. There are 8 combinations, 1, 2, 3, 4, 5, 6, 7, 8. I think I have drawn one too many. So if I want to have a truth table with 3 values A, B, C and 3 values of output X, Y, Z, or 4 values of output W, X, Y, Z. For ABC input 0, 0, 0, let us say this is something. 0, 0, 1, there is another combination. 1, 1, 1, there is another combination. I can etch this in this silicon. This is a truth table. I can implement it using reducing the corner map and then using gates that we know. We have done it enough number of times. Instead of doing that, what I am going to do is to take a piece of hardware called the ROM, read-only memory, to which I will give the input as the 3 variables, the current values of 3 variables. Each of them can have 0 or 1. That means I can have 8 possible input combinations, and corresponding to that combination, what should be the output should come out of this. Supposing the input combination 1, 0, 0, and let us say for that corresponding input combination 1, 0, 0, output should be 1, 1, 0, 0. As soon as you make 1, 0, 0, let us say this is 0, 1, 2, 3, 4, value 1, 1, 0, 0 would be written here, which I will be able to read off. This is a read-only memory. There is no programming here. I just give the value. I get the truth table. I etch it in hardware, as you will. Just if you will. Just it's a lot of. I'm exaggerating. You don't take a chisel and a silicon rock and do that. Imagine it to be a hardware truth table. Hardware truth table. Truth table is writing in paper. I give you a chisel and a piece of silicon. You etch it. That is a ROM, read-only memory. Now, how does it help me to design a combination logic? This is the way. This is the combination logic ABC input, W, X, Y, Z the output. That is what I want to implement. It could be a combination logic function or a steering logic of a sequential logic function. I use this ROM, feed ABC as inputs, and corresponding values are etched in, get the outputs. But then it is fixed. I can't change it. The programmability concept does not come in there. It is same as the original description now. So for each truth table I need to put a new etch. I have to go and get a new slab of silicon, which I don't want to do. I want to use the same hardware and use it for different applications. That means there must be some programmability. So if there are 3 inputs to the function, all the 8 combinations of the ABC can occur. There is no other possibility. So inputs are common. Whatever is the application, whatever is the variation in the outputs, there are only 8 combinations of input possible. Correct? 0, 0, 0 to 1, 1, 1. That part is common. What is different is for each combination of the input, the corresponding outputs are different for different systems. Different truth tables, different sharing tables, different combination logic functions will be implemented with different outputs for the same set of input combinations. So instead of making it fixed H hardwired truth table, I will add a P to it. So introduce this programmability here. I will write as required in my truth table every time the new value. That is the programming aspect of it. So instead of fixing 1100, I will have this 4 XS which will be changed to my requirement. So I will now get a new truth table for the given application. In that truth table, for each of the combinations, what is the value of WXYC? And those values of WXYC I should put in this position for 0, 0, 0 input, 0, 0 input 1 here. That part of that method of, that procedure of putting the different values of WXYZ for different input combinations called programming. This is programming in a sort of a crude sense. You write a program in computer. All of you are familiar with C language now, being taught as an introduction to computing. So we don't do that type of programming here. I am only changing the programmability in the sense I can select, rather it's a selectable design. Programming is a word, programmability is a change. Because it is changed, it is called programmable. It can be changed. So what is the new value of WXYZ for each of these combinations of ABC will be decided on that particular truth table you are going to implement, which will depend on the input-output relations that you want to implement for that particular system. So how are you going to make it possible? How are you going to make this programming possible? So now it's a two-step process. I have used it as a single piece of hardware where I have 3 inputs and 4 outputs. Earlier there are fixed values, a ROM. ROM is a hardwired truth table, but it is a fixed truth table. A fixed truth table has another name called lookup table. A fixed truth table has a name called lookup table. That means like a multiplication table. You can only look up the value. You can't change the value. 12 times 12 is 144. Can you change it? No. But you can look up if you don't know. Of course you don't know, so you look up all the time. And nowadays you use computers for everything, right? So that day I was finding a student using some addition, some 3 hexadecimal, 3 decimal binary numbers, wasting 15 minutes on that, programming it to get the values, because we are used to so much to computing. So fixed truth table is a lookup table where there is no programmability. But programmability has to be there for me to implement different functions using the same piece of ROM. Such a ROM whose content can be changed for different applications is called a PROM. PROM stands for programmable read-only memory. That is the first programmable logic device we are using. So that is why I said PROM, programmable logic device. Many programmable logic devices we are going to discuss. The first one of them is a programmable read-only memory. Now I have to tell you how do I use a programmable read-only memory to implement different logic functions. That means my ROM is going to consist of 2 values. PROM implementation of logic functions. Now, the first part of the ROM, I need to get all the minterms. Because the truth table, the left hand side is common. Whatever is the output, whatever is the system, the left hand side of the truth table is common for 3 inputs. There are only 8 variable combinations, 0, 0, 0 to 1, 1, 1. 4 inputs, 16 combinations. 5 inputs, 32 combinations. So that is a fixed part. How do you get? First is A bar B bar C bar, second is A bar B bar C, then A B bar C bar, okay, I am sorry, A bar B C bar, etc., etc. Finally it will be A B C. So that I should get here. A bar B bar C bar is also called what? M0, isn't it? Min term 0. I hope you have not forgotten all these things that you did at the beginning of this course. And what should be inside this? Huh? AND gates, that's all. It's an AND gate, right? I want A bar B bar C bar, I want 3 inverters and one AND gate with 3 inputs. If I want ABC, I need 3 input AND gate, ABC. So this is an AND. They call it AND array. Because a large number of AND gates to provide all these minterms. These are the inputs. Now my programmability comes only in the second half. How do you combine my minterms for different applications? For different applications, there are different truth tables, or different transition tables, or different steering logic tables. The outputs will be combined differently. For example, I may need M0, M1, M2 in one application. Another application I may need M0, M1 and M7. So I should be able to select some of those minterms and combine them as in OR gates. The second part is all these 8 minterms are available, out of which you have to choose which are the minterms required to implement a particular function W or X or Y or Z. So that will consist of OR gates. So how many OR gates must be there depending on number of outputs required? There are 4 outputs required, A, B, W, X, Y, Z. 4 OR gates in which all the 8 inputs will be fed. I should be able to retain some of them, disconnect some of them. Do you understand what I am saying? So I will draw this symbolically, even though it is very difficult to draw this 4 OR gates with 8 inputs each. Symbolically, I will say there are 4 outputs, W, X, Y, Z, which is nothing but a combination of this. Maybe I should draw it a little bigger. This OR gate is only one input, symbolically. All of these, each of these OR gates has 8 inputs, M0, M1, M2, M3, M4, M5, M6, M7, out of which I will retain those which are required for my particular outputs based on the truth table and remove those which are not required in my output. So this is WXYZ. This is an OR array, but this is programmable in the sense I can select which of those M0 to M7 will go into an input OR gate and which of them will not go into those OR gates. Those which go into the OR gate depend on the function. After having the look at the truth table, after looking at the truth table, you decide maybe M1 should go, M7 has to go, M3 has to go, M2 has to go, rest of them need not go. So only retain those connections. First I have the provision to connect anything. How many of them will use depends on my requirement. So this is an OR array. This is fixed for all designs, isn't it? So I will call it a fixed AND array. This is programmable. Each for different applications I can have it. So I will say programmable OR array. Programmable. For example, W is M0 plus M1 M3 plus M7 as an example. Then I will have to retain this connection. So whenever I find a dot, connection is retained. Whenever I don't put that dot, you assume that the connection is not put, connection is snapped. There are 8 inputs waiting to go into this OR gate. I retain some of them, terminate some of them. Whichever put a dot there, thick dot, assume it is connected. Whichever I do not put a thick dot, assume it is not connected. We have to have some understanding that. I'll say it's only hardware finally is going to work, not the board. Whatever you write on the chalkboard is not going to work. We have to make a chip. We have to make an interconnection. So M0, M1, M3, M2, M4, M5, M6 are not connected to W. Similarly for X I have different combinations. X may be M2 plus M7, M4 plus M6 plus M7. So it may be M2, M4, M6, this is only a symbolic representation. Now the programmable device comes into picture. This is a programmable device. This device, total device, where these are my inputs available. This I don't have any control over what is inside here. And up to this is a PROM. In which a fixed AND gate will produce all the minterms required, and a programmable OR array in which I can retain such as those minterms required for each of these outputs and not connect such as those inputs which are not required for that particular output. How do you do it physically? There is different technology. I am not going to get into the technology here. You will learn this some other course. You can suppose there is a fuse, like a fuse wire at home. Have you ever seen a fuse wire? So you can have a fuse wire, it can be snapped if you want to. Those who want to retain those connections, you leave this fuse wire intact. If you don't want to have a connection, you snap the wire. That means there is no connection. That means it's called fuse technology, anti-fuse technology. Fusing or anti-fusing. But then once you snap it, you can't get it back. For another application, I want to change it. I've already snapped it in my previous application. So that is not a good technology. So there's a charging and discharging. You can have a charge pocket, keep it when you want a connection, discharge it when you don't want a connection, again you can charge it. So these are all different technologies called programmable devices, which you will probably learn in your semiconductor devices and technology courses. Those who are doing VLSI technology will do this more detailed, but everybody will be doing a semiconductor devices course, solid state devices, in which you will learn some of these things. So let me not get into that domain here. Suffice it to say that there is a provision by which I can retain some of those connections and remove some of those connections and reprogram it for certain other combinations also. Because once I have retain and then remove, that does not mean that it is useless. Suppose I want to change my configuration, I want to make an error correction. Suppose I find this error, this is a small 1 or 2 mistakes in the connections, I can always redo it. So I should be able to erase it and reprogram it. It's called erasable programmable memories. EPROM. EPROM. ROM is the truth table etched in silicon, hardwired truth table. PROM is a truth table whose output can be changed as per requirement as required. An erasable programmable read-only memory is a programmable read-only memory whose programming I can erase and reprogram it for different applications or for changing a configuration or making a correction. How do you erase it? There are technologies. You can erase it by shining ultraviolet light. called UV erasable, ultraviolet light erasable technology, or electrically erasable, double E. So you can have ROM, read-only memory, PROM is programmable read-only memory, EPROM is erasable programmable read-only memory, UV EPROM is same programmable read-only memory. If you use the erasure technology using ultraviolet rays, it's called UV EPROM, or you can do electrically erasable, EE EPROM. Electrically erasable programmable. There's one other technology called electrically alterable programmable technology, programmable memory. The difference between electrically erasable and electrically alterable. I can go and change something only. Erasing means you erase the whole thing like a slate. I have a slate in which I erase it and start all over again. Ultraviolet rays will erase the whole thing. Electrically erasable, I can erase the whole thing. Whereas electrically alterable, I can selectively go and change, alter. If you want to reprogram it, or especially when you want to correct a bug, I'll go and alter it like a precision, like surgery nowadays. Really they used to cut open. Today they can point laser beam and then make a correction, right? So it becomes electrically alterable. Electrically alterable is also known as flash memory. Have you heard of this term, flash memory people use? Flash. These are all jargon today. It comes in popular magazines, science sections of newspapers. You do a lot of, you sit in front of computers all day, but what do? You don't even understand, try to understand some of these basic stuff. You are all double E's. Yes? All of you are double E here, right? Some of these things you should know, I say. These are household names today. Somebody will come and ask me how much flash. I don't know. What does he mean? But he knows what a flash is in his computer. He is not an electrical engineer. That's what I'm trying to say. Okay. Anyway. Leaving all this apart, I have this programmable feature in my ROM by which I can connect those inputs which are required in the OR gate, and those inputs which are not required in the OR gate, I will not connect them. I can change it by erasing it and alter it, and all that is possible. So this is how I have a programmable solution for my logic function emulation. Now I have a 3 input 4 output truth table to be implemented. I take a ROM with 7 min terms, connect my inputs ABC here, and get 7 output. That these connections are made by programming, so that W will represent this, X will represent. How am I going to go into that and do it? I am not going to tell you. As I said, the technology of programming and erasing, I am not going to tell you because it is not part of this course. It's too much of technology. Similarly, how do you do it in a programming in a lab? You don't open it and then look for the OR connection and then put it. You don't do that. So by externally injecting signals, currents, you have to program it and erase it, right? So there's a provision for there's a device called PROM programmer. PROM programmer. You insert this in the PROM programmer. You insert this device into a PROM programmer and type in the word. For each word, each address, this is called addresses. 3 inputs will generate 7 addresses, 8 addresses, starting from 0 to 7. Each address, what should be the value of W, X, Y, Z will be given. So I go and type the first address and write what word should be there. What word should be there depends on whether W is 0 or 1, X is 0 or 1, Y is 0 or 1, Z is 0 or 1. Then I go and change my address to 001. There again I will say what is W, what is X, what is Y, what is Z. This is called programming. So I have a device, a little equipment. It's called a programmer, PROM programmer, in which I insert this little device, ROM, PROM, and then first type the address and corresponding data into that. So these are called addresses. So ROM content will be. We make a ROM content table. So address Address is nothing but concatenation of the ABC inputs and output word. These are not any different. There is only jargon here. So here I have ABC, here I have WXYZ. So 000 address will have whatever 1 0 1 1, as I say, as an example. Don't take it too seriously. And then I will say 001, something like this. This art of doing this is programming. Art of putting this ROM content table into the ROM physically, electrically rather, is called the programming aspect. That can be done by a simple device called a programmer, wherein you insert your ROM and type in the address and corresponding data. So this is called the address, this is called the content. I have already said address. So address and the corresponding content. So ABC has no meaning here. It's only for your mapping. Address has ABC, output has WXYZ. You don't write in binary, you write in hexadecimal usually. Usually ROM content table is written in hexadecimal form. Because remember, these are all very tiny examples I am giving in the class. I don't think anybody will use a 7 word ROM. ROM with only 7, 8 words and 4 outputs. Usually in a big system, you may want to have several inputs and several outputs. So if I start writing zeros and ones all over, it becomes too confusing to handle. So you usually write in hexadecimal. So this will be in hex. In hex you should write. It will be 0, 1, 2. ROM content table in hex. So I will say 0, 1, 2, address, content. Corresponding to the address, what is the content? Hexadecimal, hexadecimal, hexadecimal. 7, 8, 9, 10. After 9, what? A, B, C, D, E. And for example, this is called 1011. 1011 is how much? 1011 in, how do you represent hexadecimal? After 9 is, instead of 10 you get A, 11 is B, 12 is C, 13 is E, 14 is F. Oh, I'm sorry. A, B, C, D, E, F. So 10, 11, 12, 13, 14, 15. So this is B. Second is 8, so forth. So I'll give you an exercise now. Remember that 4-bit binary to 7-segment converter we did? 4-bit binary BCD to BCD to 7-segment converter, decoder, BCD to 7-segment decoder we did earlier. Take it and put it in a ROM. Get a ROM content table for that exercise. Don't make it BCD, make it binary. Understand? The problem is I have a 4-bit input in binary. Go from 0 to F values, and the output will be 7 segments. So I will call this A, B, C, D, E, F, G. You draw a table 0, 1, 2, 3 up to F it should show. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. For this, can do a ROM design. That's a homework assignment. You have to get a one single ROM can do this job, right? You need 4 inputs A, B, C, D and 7 outputs A, B, C, D, E, F, G. And then for each of this address 0, 0, 0, 0, whether A should be, A is a segment, you know the segment allocation, you know, just redefining the problem for you. So for each of these characters, you want to know whether A is on, B is on, C is on, D is on, E is on, F is on, G is on. Which is on, which is off. On is 1, off is 0. Write the table and then that will be the ROM table. First write it in binary and then convert it into hexadecimal. Hexadecimal will have 0 to F as the address. So I want you to give me the final answer like this: 0 up to F address. Content would be 7 bits, isn't it? Content will be 7 bits. So how do you write a 7-bit hexadecimal? First 4 bits, LSB, 1 hexadecimal digit, 7-bit table number. For example, if we have number 111000, this is 0, this is 7. Isn't it? This is called hexadecimal 70. Like that, for each of these things, I want you to get the corresponding hexadecimal. So ROM design is one of the simplest designs possible. Only thing you need to know about a ROM design is, once the problem is given, you should ask for the correct size of the ROM. How many inputs, how many outputs. For this problem I needed 3 inputs, 4 outputs. For this problem I need 4 inputs, how many outputs? 7 outputs. So first thing in a ROM design is ask for the correct size. Size of the ROM given as 2 power n times m, where n is the number of inputs, m is the number of isn't it? 3 inputs will have 8 rows. Each row will have 4 outputs, W, X, Y, Z. So 2 power n times n, 2 power 3 times 4. What is the size, units of size? Huh? Unit, every size should have a unit, right? Bits, why bytes? Byte is what? 8 bits. Where is 8 coming into picture here? It's bits. 2 power n into m bits. Once you have the size of the ROM, get the truth table, ROM design, PROM based design. So whenever I write ROM, you write PROM, because the ROM is once only. Like your multiplication table is fixed. ROM comes from factory. Supposing you have a equipment in which everything is tuned and then they don't want you to meddle with that. They'll put a ROM. You cannot change it. You cannot erase it. You cannot change it. Factory programmable it's called. ROM, when it is programmed in a factory and you will not be allowed to alter it. Supposing I have some program which comes the system program. As soon as you switch on the power of a computer, so many things happen before you can really start typing your keys. All those things I don't want individuals to do it, because then everybody is doing it a different way. It will work, it will not work, and you will blame the company for not designing a proper computer. So they put that in bootstrap RAM. You might have heard of this. Have you heard of this? Boot RAM. RAM is in which they put all those initial programs. And some of those companies, that is the proprietary item, because you can always put whatever you want, junk, and then you can claim that your computer is junk. So it's a proprietary, this patent comes from the original ROM in which they are able to do everything, system level. Similarly, in a music synthesis, as soon as switch on, of course you may want to do it your own music, but then there will be standard music, right? Yankee Doodle, something it starts, as soon as you switch on. That is again is programmed in the RAM, they won't change it. Yankee Doodle, no, you have not heard of it? There's all these American rhymes, like right. Like that. These are all fixed. So in a calculator, sine table, cos table are programmed. If I ask you to put your own sine table and cos table, it will be catastrophe. So sine table and cos table comes, so that when you say sine and 37 degrees, it promptly comes a number, because it goes and looks up the value of 37 in the ROM table, lookup table it is not a programmable table, it's a lookup table. The value of sine is coming out and you use it for your computation. So PROM, you get the size and then get the truth table, write the ROM content. You don't call it PROM content table, it's called ROM content table, even though it's PROM. Next step is to get hold of a programmer, program PROM in a programmer, in a PROM programmer. Those who are industry people who have been doing this for a long time, they'll say, burn the ROM. Have you burnt it? That's all this pet jargon they use. Burning a ROM is putting the program in it. It will burn anything. See, they're assuming there's a fuse which are flowing and then it's going up in flames and all. It's all imaginary. Putting a 0 or a 1 there, called programming, it's also called burning. In colloquial terminology, if those designers who do it all fun, it's burning. Have you burned the ROM? That's what it is. If your ROM is wrong, you'll have to burn your exam papers. Make sure that you don't do it, it doesn't happen to you. Okay? So this is programmable. So I gave you a twofold treatment today. I wanted to introduce you to the concept of large-scale integrated circuits and reason for programmability, and also the ROM as a technology. ROM, PROM, erasable ROM, erasable programmable ROM, and all that. There are other programming devices. We did a simple example, and I asked you to do one more example. So the next programmable device is called Programmable Logic Array, PLA. We'll talk about it in the next lecture. Programmable logic arrays in which a similar programming feature is built in, but how is it different from ROM, PROM, and how is it more efficient than PROM? We'll see tomorrow in the next lecture.